Welcome to the podcast of Data and Analytics in Business. We will learn from the leading industry experts using data and analytics to solve the problems and create values in practice. We will also learn where the industry is heading to and how data and analytics will shape the industry in the future. Most importantly, how they are preparing their business for digital transformation and disruption in the future. I'm your host, Jason Tan, and thank you for listening. Hey guys, thank you for listening to the Analytics Show podcast. I really appreciate your support and feedback on our podcast. So just a quick shout out. This episode is sponsored by us at the Analytics Show podcast. So whenever you are listening, follow the link in the description to join our second giveaway, but also the first giveaway of 2022 to win 1 million Shiba Inu, guys. So I want to give away 1 million Shiba Inu, guys, and so no matter what price it will be, you can guarantee to get 1 million Shiba Inu coin. So start off the year right by standing a chance to win 1 million of the most promising cryptocurrency of 2022 as a small token of our appreciation for your support. It is a new year and a perfect time to start your new plan for your analytic career. So hop over to the Shiba Inu Troy before it raises up to the cryptocurrency mountain while listening to the podcast. Thank you so much. Bye now. Hello, thank you so much, everyone. Welcome to the Queensland Advanced Analytic Meetup event. So today we have got Simon
O'Toole.
Presenting about what is happening with the telescope and the astrophysics. It's probably the topic that I obviously have zero expertise, so I'm really looking forward to see the presentation today. So the presentation is probably about 30 to 45 minutes long, and then we probably have just 50 minutes Q&A. Just want to say just very quickly for the shout out, the meetup event is sponsored by the Analytics Show. So it's a podcast where I interview business leaders around the world, how actually they use data science to improve and run a high performance business. So if you got a chance to, feel free to subscribe. Speaking of that, Simon, I should totally get you to the podcast if the opportunity allows. So
that would be great.
Without further ado, please take it away, Simon.
Okay, thank you. I'll just share my screen and hopefully, let's see, there we go. Has that gone the wrong way? I think it looks like it's sharing the wrong way. Let me see if I can, hang on, I'll stop. That when in doubt. Desktop one. Not that one. This one. There. Oh, come on.
I think you were pressing something on that button and then it works perfect. I think, it's good over here. From what I can see,
okay.
The main screen of the presentation.
So can you see just the single screen?
Yes.
Just the single screen. Let me see if okay, good. Okay, well, hopefully that's it then. Okay, well, thank you again for the opportunity to speak to you, to your group. So this talk, in some ways, I mean, I gave it originally at a data engineering conference in October. So it does come at it a little bit from a data engineering perspective, but what I wanted you to do is to start to think about some of the data analytics possibilities that you might see there around this. So I'm going to talk about how we move quite large amounts of data and ever increasing size of data from telescopes in remote locations to data centers in more accessible places. And so this is adventures in astronomical data pipelines. And so I'm from Macquarie University, the AAO, and we run a project called Data Central, which is the main thing that I'll be talking about. But we do work with folk at the Australian National University, NCI, which is the National Computing Infrastructure Facility, which is a federal government funded body through something called the National Competitive Research Infrastructure Scheme, or NCRIS, and Astronomy Australia Limited are our sort of funding agency that deals with all of the finances and a lot of the paperwork, so that we don't have to. Okay, so who am I, and what is Data Central? So before I became sort of involved in data engineering and data science, I was a research astronomer for 15 years. I worked around the world, in Germany, and I've spent time in the US and Denmark as well. Astronomy is a very international subject. Most countries have some form of astronomy department in their at least one university, and a significant number have sort of researchers doing all sorts of cool astrophysics and studying the universe and looking for life and all of those fun things. So right now I'm based at the AAO, which is in Sydney, and is now part of Macquarie University. I was just saying to Jason before that we have had many different guises over the years, and we were originally jointly funded by the UK and Australian governments. Then we were solely funded by the Australian government, and then now we are part of Macquarie University. And that's probably one of the better outcomes. So we're pretty happy where we are for the most part. And Data Central itself is an e-research platform that we've developed, and the main goal is to help researchers manage their data, publish and share and analyze it. And we aim to support the full data lifecycle from the telescope, which is what I'll mainly be talking about here, but also a lab, just a research lab somewhere, all the way through to where the data is published in a journal article, and that is often like the interpretation and what does this mean and all these things. So, in a lab, you might think of all of the COVID-19 vaccines and all of those sorts of things. All of the measurements are done in a lab, and then the papers get written up and published and reviewed by other scientists, and then published in journal articles, and then they start to develop vaccines commercially. So we aim to support all of this whole process, and from a research point of view rather than a business point of view, because researchers don't have lots of money. So the background and motivation from the astronomy point of view is, so astronomy data is really, you can think of it as classic big data. So originally big data was just the 3 V's, volume, velocity, and variety, but now we've expanded to include, of course, veracity and value. So in terms of volume, we have a very large range of sizes of data. So for 47 years of the Anglo-Australian Telescope, or the AAT, which I'll talk about again in a moment, we have 15 terabytes of data. So not really a lot over quite a large time frame. Moved to more recently, the last 8 or 9 years of the Murchison Wide Field Array Telescope, which is over in Western Australia, has generated 40 petabytes of data. And in fact, it's generated a little bit more, but they actually, at the Pawsey Supercomputing Centre in Perth, they have a 40 petabyte quota cap. So that's all they can actually host. But in the coming years, probably towards the end of this decade, we'll have the Square Kilometer Array. And in 1 year of data, and that will run for probably 20 plus years, in 1 year of that facility, it will generate 600 petabytes of data, and that's the data that is saved to disk and made available to researchers to access. So it will generate more data, but a lot of it we have to process and throw away before we can store it, because the volumes are just too great. Velocity, so the Anglo-Australian Telescope generates no more than about 15 gigabytes of data per night. So not an enormous amount, and it's often much less than 15 gigabytes even. But the SKA, on the other hand, will generate approximately 1 terabyte of data per second. So as you can see, in the next few years, we've got a lot of things to work on, including there'll actually be a lot of data science opportunities here to understand how to reduce this data and to process it in a way that we still keep the important science and the important results that we're interested in, without necessarily having to keep all of the raw ones and zeros. that the telescope collects. And then, of course, variety, we have the raw data, the data that really the telescopes themselves collect include images of the sky, spectra. So that is when you disperse the light into sort of a rainbow fingerprint from a particular object, a galaxy or a star, and the spectrum gives you an idea of what the star or the galaxy or planet or whatever might be made out of, or things that are going on inside it, its movement and that kind of stuff. Voltages, so radio telescopes can also, that is sort of the raw data is actually a voltage, but then you have to do a lot of processing to convert it into something more meaningful. And there's something called visibilities, which is when you combine, you can see the images actually here on the right. These are two different telescopes. On the top, you have the European Southern Observatory's very large telescope with a nice 4 lasers shining into the night sky. And in the bottom, you have the Australian Telescope Compact Array. And then what researchers, what astronomers do is they actually take the light from each of these telescopes and combine it to create one image. And it's quite a complex procedure. It's actually more straightforward in the radio telescope at the bottom than it is in the optical mirror telescope at the top, because with radio telescopes you can basically turn everything into a voltage and then convert, play around with things after that. Whereas in an optical telescope, you have to actually have the beams of light moving around. Then we also have veracity, and that really in astronomy, in the astronomical sense, is to understand and remove the sort of the fingerprint, the effects of the instruments and the telescopes that you're using. So every time the light bounces around and goes onto a detector, you add some kind of systematic effect. And particularly in radio telescopes, you've got radio frequency interference is a very big issue to deal with, both within the telescope and then just ground-based as well. So just as an example, there was a classic case of this very fascinating astronomical occurrence that people measured a few years ago, and no one understood what it was, and they had conferences about it. It was all very exciting and mysterious until someone realized that it was actually just someone using the microwave in the visitor center when they weren't supposed to, and the telescope was just picking this up as a very large glaring signal. So yeah, we have to make sure that we understand the data that we're taking, and that it is really of stars and galaxies, not just of telescopes and cameras. And then the value, and the primary value, of course, is expanding human knowledge. But the cost of running some of these facilities is quite high. So the Anglo-Australian Telescope is probably around $10,000 to $15,000 per night, which compared to, say, the European Southern Observatory at the top right here, that's probably more like 100 to 150,000. I was probably about 100,000 euros per night to run those telescopes. In fact, per telescope, that might be. But then moving into the future, the square kilometer array will be probably an order of magnitude more per night. So you're looking at many hundreds of millions of dollars just to operate these facilities. Okay, and so to now talk just a little bit about some of the astrophysics that I'll be that is sort of driving what we're doing here. So you can think of, for the purposes of this talk, that astrophysics can be divided into two parts. Time critical science, so things that go bang, and then you can see in the top picture there, something's gone bang, it gets very, very bright, very, very quickly, sometimes over hours, but usually over a few days. But in the timescales of the universe, that's very, very quick, and then they fade away as well. And so you really, if you want to understand them, ideally you want to catch it before they go bang, so as it gets bright, but then also look at things as they fade away, because that will give you an idea of what has actually happened and what was the thing that made the Big Bang, basically, in this case. And then there's everything else. So there may not be a bang, but sometimes you might need timely data as well. So here, just in the bottom of this, these images on the right is just actually two galaxies merging. It looks kind of like one, but the weird shape of it is sort of and the sort of it looks a little bit distorted. Is in fact two galaxies merging, and the gravity of those two over very long time scales, I mean hundreds of millions of years, is causing all sorts of interesting effects. And the one on the right actually is two different wavelengths. One is the blue and green is from a radio telescope, so not very high resolution, but that's what you get with radio telescopes. And then the sort of the grayscale image is the something taken with an optical telescope with mirrors and lenses and things like that. But these are large scale, the 8-meter mirrors as the primary mirror for these facilities. But with this one on the bottom right there, you see it's actually a cloud of gas that's expanding over time, and over the course of 20 years, you can actually measure that change. So yeah, not time critical, but it is important to periodically look at these things. And there are other things that might vary, change over the course of minutes to hours or days, but they're not. There's lots more of those, so they're not as essential. So for this talk, we're focusing on the time critical, but everything else is no less important. And so really the things that we're talking about are explosions and collisions and mergers. And the two key use cases here are the merger of black holes and neutron stars. So that's sort of the illustration, the cartoon on the top, and supernova explosions. And that's where a very large star, maybe 10 times or 20 times heavier than our sun, after a very short life of a few million years, becomes too unstable and explodes, and is very, very bright, and for a very short time is the brightest thing in the observable universe. And so you may have heard of gravitational waves. There was a big splash about those made a few years ago when the first gravitational waves were confirmed as detected. These are something that comes from Einstein's theory of general relativity, and it was really the last key prediction of his theory of general relativity that had not been verified. And so astronomers were able to verify this the way they measured the merger of two black holes. So very massive, dense things that were spiraling around each other like this, and they got closer and closer together and then merged, and then they caused these ripples in the space-time continuum. So yes, actual science fiction made real. But the key thing is that almost immediately for this, you need to observe, you need to make observations. So you understand what is actually going on. So you need to therefore process the data quickly, and then once you've done that, you'll have a better idea of what you need to do to understand it, to follow up. And the research fields are very, very competitive. So the people who detected the gravitational waves that I mentioned at the beginning here won the Nobel Prize for Physics 2 or 3 years later. So, and that's, huge prestige and huge, big money prize, all these sorts of things. So very, very competitive to understand. And in fact, the supernovae at the bottom, there is one type of supernovae that had previously won the Nobel Prize in 2011 for their use in understanding how the universe is expanding and the rate at which it is. So now to get into a little bit of more data talk. So data format. So observational astronomy uses something called the Flexible Image Transport System, or FITS format. This is maintained by NASA at NASA Goddard and the International Astronomical Union, which is not like a trade union. It's actually just like the professional organization for astronomers. And so this standard describes, how data should be stored. And a FITS file contains a minimum of an ASCII text header in the format you see here on the right, which is basically, it's often you can consider it key value pairs, but it's really key value and comment or description. So that is the primary format used, and then there's a binary image as well, and so that contains the actual data. The header contains the metadata, and the image, the binary component, contains the actual image, the thing you've observed. You can also, in fact, have multiple headers in one file and multiple images, and then there are binary tables, and it sort of gets in a little bit complex. But for the most part, you can think of it as a text header and a binary image. We do use other formats, particularly for transporting data. So CSV, your classic data format that's compatible with everything, and then HDF5 as well, and that they are used. HDF5 is really like a big container, so you can think of FITS as like a big container as well. HDF5 is even more general, doesn't have as many standards wrapped around it, and those are used to move data around. And then we use Apache Parquet format often, increasingly to store the data, because it stores it in a sort of a columnar kind of way. Data acquisition. So observations, when you're doing astronomy, you require two components. You are looking at science frames, so where you're actually taking the image or the spectrum or whatever of the star, galaxy, planet, etc. And then calibrations, because as I said, in order to make sure we have veracity of the data, you need to understand the instrumentation and what that may imprint on the data itself. So that's the calibrations, and there's a whole lot of different sets. And then if you are doing spectra, then when you're dispersing the light, as I said, into the rainbow fingerprints, then you need to provide some kind of way to calibrate that, to say what is wavelength. So what is the blue part? What is the red part? That kind of information is also required. The observations are made using something called the World Coordinate System Convention, and this defines celestial coordinates on the detector on the chip. And the chip that we use is not the same as a CMOS detector that you might have in your mobile phone or in a digital camera, although we're starting to look at that as well. But we use something called charge coupled devices, or CCDs, and they are typically cooled with liquid nitrogen. That's for optical. If you go out into the infrared, then you need things that are cooled by liquid helium, and this slightly different manufacturing process. But as I said, all the data goes into the the metadata goes into the FITS header. So this is where our problem is. So telescopes, as I said, need to be in remote locations. So you either need to have them very radio quiet, no mobile phones or microwave interference, or you need to have them very, very dark, so no artificial lighting. So that means they need to be far away from, a lot of electricity, or you need some, obviously, but you can't have built-up towns and that kind of thing. So that's where a data center can't be so isolated. You need proper power. You need reliable power. You need people to be able to access it regularly for maintenance and the like. And then you need good internet connections, and good internet connections in remote areas are very difficult. So this is the problem. So what we need then is an efficient way to move the data from these sites, which are many hundreds of kilometers away, to the data center. So the case study for this talk is the Anglo-Australian Telescope, which I've already mentioned a little bit. It's a 4-meter telescope, 4-meter mirror in central New South Wales. And the data typically consists of some number of 32 megabyte FITS files, and that number depends on the number of cameras that you have for whatever instrument that you're using. It could be 1, 2, or 4 typically. There are 2 instrument control computers depending on the instrument that you're using. So this is a spectrograph or just an imager taking pictures, and these control the cameras as well. So even with the spectrum, the initial, data is taken with a camera. And as I said, there's limited compute and storage capability on the mountain. I mean, that it's becoming a little cheaper and a little easier to do, but it's still just about maintainability and access. And so really having if you need to use a supercomputer, for example, to process data, you can't have that on the mountain. So fewer astronomers now also visit the telescope. So this telescope, you can go on a tour. So it's probably about 8 hours from Brisbane. If that's where you are, it's about 6 hours from Sydney. So you just go down the Newell Highway. And in October, in the October long weekend, they traditionally have an open day. So you can go and have a look and listen to talks and lectures and everything like that. So if you're interested, I certainly encourage you to do that. Hopefully this year COVID allows it. But these days we mostly operate this telescope in other facilities around the world remotely. And in the case of transient astronomy, so that's where the time-sensitive data comes in, time-critical, astronomers don't even go to the telescope or do anything from their home university. Someone else takes the data for them, packages it up, and sends it off. And that's where we come in. And so we need a way to move and store data securely and process it rapidly with a very limited budget. These are, given the complexity and the scale, these are projects that typically have hundreds of thousands of dollars per year, not millions. And that includes things like infrastructure as well. So it's for historical reasons, this has not been seen as critical but that is changing, and I'll show you why in a little while. So Siding Spring Observatory, as I said, it's about 470 kilometers from Sydney. It's probably more like 700 kilometers from Brisbane. It's about 560 kilometers from Canberra, and Canberra is where the NCI facility is, where we also move data to. So we have got a single 10 gigabit pipe that runs from Siding Spring Observatory to our main trunk in Coonabarabran, which is the nearest town, and that's where the Australian Academic Research Network comes in. The data, basically, there is a connection between all major all universities in Australia are on the on ARNet, and we pay a subscription fee and get access to these large pipes of data, including some of them are up to 100 gigabits. But so anyway, we have to move the data around, and this is the complexity. So our solution, we use Apache NiFi as a transport system to move the data from the telescope to the AAO and NCI. We then pass the FITS header and place the ASCII components into a database, Mongo database in this case, and then we use some web technologies to query and download it. We do need some authentication because we want to make sure that the people who are accessing the data should be. Some of the data is actually proprietary for a few, maybe 12 to 18 months, and then it becomes publicly available to everyone because it is publicly funded for the most part, after all. And then the data processing or reduction, we use a combination of Docker and some bespoke software, which I'll discuss in a moment. So here's a summary of the technology solution. And so if you want, I can make the presentation available to Jason afterwards. And so this will include links to all of these different things. So Apache NiFi, I'll talk about each of these in a little bit more detail. So NiFi, it's described on their website as an easy to use, powerful and reliable system to process and distribute data. It was originally designed and written by the US National Security Agency under the name Niagara Files, and then they released all of these, a whole lot of code in 2014, and much of the software development is now done by Cloudera. So if you've used Hadoop and MapReduce and Spark to speak to Hadoop systems, you'll probably have come in contact with the Cloudera managed system. So the good thing about NiFi is it understands many data formats and storage systems natively. It doesn't understand FITS, but that's okay. It doesn't really need to, but understands databases and file transfers and these sorts of things. And it can be set up as a cluster using Apache Zookeeper or as a single standalone system. You can also run it, you can have multiple servers speaking to each other, or you can have client-server based systems using something called Minify. And the good thing one of the things I really like about it is it uses a GUI to manage workflows. So each of these little boxes that you see here is a stage in the data processing. And in this case, it's once we've actually received the data in Sydney, but there is an equivalent model for the telescope as well. It's just not quite as complex. So you can have forks and branching and all sorts of different components here. So you can move files, you can move database entries, and things can be as complicated as you need them to be. And the great thing is that you can add processing and scripts along the way to manipulate the data as you require. And in some cases, you may need to do cleaning or something like that in order to get data properly into the database. So MongoDB, some of you may be familiar with MongoDB. We're using just the community edition. As I said, we're very low budget, and we basically store the metadata as a document with a sort of a nested structure. The original FIPS header goes in as a subdocument, and then we have one of our key requirements is interoperability with other data centers, and so then there's another subdocument that sort of handles that. So MongoDB has got geospatial features, but as I said, the world coordinate system is very complex. It's not the geospatial S2 library that Mongo uses is not quite sufficient. You can sort of get around it, but it's a bit complicated. So we're considering a project to add the sort of the standard library for world coordinate systems, because MongoDB is actually an open source project, so it does allow you to develop things, and it has got optional coordinate systems. So this would allow us to basically look for a point in a circle, which is kind of what you see in this image with the crosshair in this circle. Find everything inside that circle, basically. The Central Authentication Service, it just is a very useful thing. It was developed by the Apereo Foundation, which is founded by a bunch of universities around the world, and it allows you to authenticate and do access control using a bunch of different protocols. It has its own native protocol, but OAuth to SAML you can delegate to other systems like Google and Office 365 and Salesforce, and whichever you really want. And it's very, very customizable. And not so straightforward to set up. So when I say out of the box, there's still a bit of legwork to do, but the basics are pretty easy to do. Web technologies, we're just using React, which of course is one of the favorites of current web developers. This is where we handle query from astronomers. They want to get access to data. They can query on position on the sky, time of observation, all sorts of other things. And then we use REST APIs to handle the actual querying and pulling data out. So data reduction, this is where we actually take, I'll show you sort of the before and after in a second, but we take the raw data and we process it, we extract it, and get something that scientists can actually use. And we're using Docker for this, and Celery, which is sort of a batch mode, a batch system that allows you to spawn off a whole lot of different jobs at once. And the big challenge for us is that the software that is used to process a lot of this data is written in Fortran 95. And it's a legacy system. It's 20,000 lines of code. So it's very difficult to port to something more easily maintainable, because while Fortran 95 is a great language and its subsequent generations, it's very good for number crunching, there are fewer and fewer people who are learning how to program in it. And so we do need to write a lot of Python wrappers and that kind of thing. And there are others in the astronomy world that use R to wrap some of the Fortran as well. But it does allow that using this model with Docker and Celery, it allows us to do parallelization and process data quite rapidly. So in a single server with 2 CPUs, we can process 120 gigabytes of data. That's many hundreds of, it's about 1,000 science frames, plus for every science frame, you typically have 3 or 4 calibration frames or more. So in 45 minutes. So we're pretty happy with that. So this is the raw data on the right-hand side. So what you see here is an image of 400 different spectra of galaxies in this case. And you can see different bands here. I don't know if you can see my mouse, but there are these. So the spectra are going top to bottom. And the curved sort of lines that you see here are mainly actually features from the Earth's atmosphere and the night sky, not so much. Some of it is definitely from the galaxy. And then once you do all the processing and reduction, you get this simple spectrum, which is basically the two-dimensional, wavelength versus flux, some amount of light that is received. And then you can determine a whole lot of information from that. And I just wanted to highlight one of those. Here is called the Redshift and that's kind of a proxy for distance and time. And so the distance as in how far away this thing is, so the higher this number, so this 0.13487 is not too close by, but not super far away. The most distant thing would have a detected thing would have a redshift around 8 or 9, and that's something that is, and then because it's so far away, and light has a travel time of 300,000 kilometers per second, it's a proxy for the age, some distance in time as well. So they call it the look back time. So for a redshift of that number there, you're probably looking at maybe a billion years, or 600 or 700 million years ago is when the light was actually emitted from the galaxy that was measured. And then you go all the way back to about 300 million years before, or 300 million years after the Big Bang. So that's about 13 billion years ago. So it's sort of this, it's quite a complex thing, but then you see other things like the mass of the galaxy and all sorts of other things, how many stars or the rate of formation of stars, etc. So the future challenges, and this is where things start to get very interesting because the volume of data starts to explode. So the European and Southern Observatory, we're starting to work, Australia's formed a strategic partnership with this primarily European group, and we're working closely with them on a lot of their data projects because that's where our expertise is, and data processing. And the Very Large Telescope, very unoriginally named Very Large Telescope, and then the even less originally named Extremely Large Telescope. These are the two things on the horizon for us. Very Large Telescope is currently in operation. It has an instrument called MUSE, which I really can't remember, sorry, what that acronym stands for, but astronomers have terrible acronyms. So it's an instrument, and it has 24 cameras, and you can actually see, I don't know how clearly you can see here in the back, all of these tubes and cables and everything like this. These are all of the cameras, all 24 of these cameras. They're 16 megapixels, so they're not enormous, but there's 24 of them, and they have continuous flow cooling. So that's what these tubes are doing. They're pumping liquid nitrogen through them to keep them cooled to about minus 120 degrees Celsius. And that reduces the background noise. The instrumental noise is much reduced, and so that means you can look at very, very faint things. Because if you just went and used the 16 megapixel camera on, a digital camera, if you go out at night, it's pretty sort of fuzzy, and you start to see like this multicolored, staticky kind of noise, and that's what we're trying to reduce with the cooling. So for each exposure here, you get 1.5 gigabytes of data, and that's a science frame, and every science frame needs multiple calibrations, as I said. And then, in fact, when you want to observe some of these distant galaxies, you actually need to take multiple observations of an object, and you just move the telescope very slightly around, and that means that you can also remove some of the instrumental and telescope effects. So you end up with probably for one object, you might have about 30 to 40 gigabytes of data just for one observation. I mean, it's multiple frames, but from one sort of science observation of a galaxy in this case. And it's at Cerro Paranal, which is in the northern part of the Chilean Atacama Desert, where it's very, very dry. It's 2.5 kilometers above sea level, so it doesn't rain very much, also in the desert. And then so they move the data to Santiago, to Munich, and then soon also to Sydney. And this is the big challenge because the data processing or reduction requires machines with at least 256 gigabytes of RAM. You can't do this easily in AWS even. You can't do this on your laptop. You need dedicated machines to do that. And that's one of the other services that we provide, machines with up to a terabyte of memory just to do this kind of number crunching using many, many, many cores as well. And then beyond that, in the next couple of years, we're going to see something called the Vera Ruben Observatory, which is an 8-meter telescope, but similar to the VLT that I just mentioned, also in the Atacama Desert in a different part at Cerro Pachon. And the goal of this project is for 10 years to observe the whole southern sky. So every part of the southern sky we can reasonably see every 3 nights in 6 different colors. So it's actually images rather than spectra, but they are therefore much bigger. You have a cooled, once again, liquid nitrogen cooled, this time 3.2 gigapixel camera. And so what that gives you is 30 terabytes per night of raw data, including calibrations. But the challenge here is that we need to move the data away, and it requires data reduction on the fly, because one of its key projects is to look at transient phenomena. And so they are 2 things. There are the things that go bang that I've talked about, but also the very beginning. Probably not many of you were on the line at the time, but Jason and I were talking about the movie Don't Look Up, and that's all about detecting transient asteroids and things that might hit Earth. And so that is actually, for this telescope, one of the key science sort of goals is to understand all of the asteroids that are going around and which ones might cause us, give us trouble. So it's a 10-year survey, and we'll end up with about half an exabyte of processed data. There's a lot of work going into the data analysis and everything, but there will be so much data here that so data science is essential here, because no group of people can analyze this volume of data in a reasonable time. And they are very lucky because they're funded through the US government, through the Department of Energy, that they have dedicated fiber just for this telescope to move data from Chile to the United States, with help from Google. And then on Christmas Eve last year, it was announced that we will, some of the data will come to Australia, and we'll be involved in that project as well. And then the final, my final sort of point here before my thank you slide is the square kilometer array. This is, still blows my mind, this project. It's going to be a very large number of these. You see the things in the bottom right here, sort of might be a bit shadowy, but they're called dipoles, but they're basically like antennas. And there'll be many thousands of those spread across primarily this Murchison Shire, this where it says MRO, operated by the CSIRO. Very low population density, but 800 kilometers from Perth, which is where the processing center is. So the square kilometer array has been working, and Pawsey has been working with Cisco to develop the fastest links they can. At the moment, they have 200 gigabit fiber connection that runs for all 800 kilometers. And the data rate at full size of this facility, and it won't just cover this Murchison area. There'll be dipoles, they're called, these antennae, across through the desert as well, including stretching as far as sort of New South Wales and Queensland, and possibly some in New Zealand, I think, too. So the data rate will be 8 terabits per second. So as I mentioned before, 8 terabytes per second. So in order to actually handle this, there is no way that we can handle this data volume, because that's 8. So a terabyte per second is 86.4 petabytes per day. So the only way we can handle this data is to do processing on site. So when the data is combined from all of these dipoles and in Perth, and then store the remainder. So, and then we have the challenge, and this is probably where a lot of you guys might come in, of actually trying to understand the data and do some of the data science. So astronomers we would just call it statistics, but so data science is obviously more than that. So it's a combination of the statistics and the astronomical knowledge, but we will almost certainly need a lot of data scientists without astronomy backgrounds to understand some of the algorithms and the things to manage this volume of data. So hopefully I've inspired you a little bit to go and learn some more. And I'll say thank you. I'm on Twitter, and the team, of course, it's more than just me, is a whole group of people, some based in Sydney and some based in Perth. So thank you. Thank you very much.
Thank you so much for the presentation, Simon. That was fascinating. I think my mind was running like thousands of miles of just trying to goes around about all of those things, exactly how that works. So for everyone else, please feel free to jump on and have question. I think overall he just put his hand up for question, I presume. Or so please feel free to jump in to ask away your question. If not, I'll probably just ask a few questions to help this. I was thinking like the amount of the data that you have to store, like you say, is extremely large, right? So how do you come to decide and find a balance where you need to store the data to certain years so that you can open it up for the public, number one, but you can also use it for important event, considering that some of these things maybe will not hit Earth until a few years later. But at the same time, the crazy amount of the storage that you require. How is that balanced then?
That is a really excellent question. And at the moment, I know that, so the square kilometer array, that's where the data problems really are. So for the Vera Ruben Observatory, sort of the second of the three that I talked about, I'll start there. So they've been working a lot with Google, and there is also a very large supercomputing and storage facility. I'm going to say it's in Colorado. I'm not 100% sure. That's the NCSA, National Computing and something. I don't even know what it stands for, but it is a very large. It's one of the largest sort of publicly funded supercomputing centers, and that's where they'll be storing a lot of this. And yeah, we do need to be able to provide access ongoing into the future. The Vera Ruben, as I said, the process data in the end will be around 500 petabytes of data, and that hopefully by the end of the survey will be a lot cheaper and easier to maintain and manage. The square kilometer array, they've actually started talking with Microsoft because Microsoft are working on something called DNA storage. And it's very exciting. Basically, the physical volume to store an exabyte of data is some tiny, fingernail-sized thing because of the way that the storage works. And we ran a workshop a few years ago where they first presented this to us, and they said that probably around now we might start seeing it more commercially viable in the next year or two. So I'm hoping this year to hear more about it. But they said because it's DNA, if they can keep it cooled at the right temperature, it should last as long as DNA. And they've, pulled DNA out of, liquid amber from dinosaurs, so millions of years. So potentially, so then it's just the infrastructure and the cost of running that facility, but potentially, that might become very feasible, and so then our data storage problems will be solved. Otherwise, yeah, certainly silicon is a lot, or spinning disks. Solid state, you can't really do this. You need spinning disks and tapes. So at the moment, the solutions are around very large tape drives that have smaller solid state disks that act as a cache. So frequently accessed data lives there, and everything else gets pushed onto tape to be pulled out on request, and it's then like come back tomorrow or in a couple of days kind of thing. So the data challenges are enormous, definitely. And actually it's the access. Like, how do you search through the data? What algorithms will search through the data in a reasonable time? I can put in a query, but if you've got a catalog that's 2 petabytes, how do you efficiently query that and extract something useful?
Exactly.
Yeah. So this is actually probably the biggest challenge is the data science challenge here, because the storage is hard and expensive but manageable for the most part. It's then providing access to people, like doing the science, and that's why I said that at the end there that it's really the data scientists, it's you guys that will be leading the forefront, because even just extracting data and transform, like ETL is the big challenge here, to clean it up in a way that is then useful for a scientist to come and run their own algorithms to say, and maybe combining a scientist algorithm with a data science algorithm to actually get something meaningful out in reasonable time, because you can't wait 6 months to do this because someone else will want to access it too. So
That makes sense. In that case, I'm going to jump to my third question instead of the second one in terms of the data science and processing those data. My question then is, I can't imagine, number one, people will be sitting there to observe like just the movie. To observe the screen all the time, because that is number one. Number two, even with the recorded data, like you were saying, that processing the data would take significant of time. So the question then is that already an algorithm where it do all the trend analysis or pick up the observation, etc., in a way that it will flag to the team to say, hey, I think you need to look at this particular time at this particular hour, this sort of thing?
That's a great question as well. And certainly people are working on these algorithms. I don't think there's anything set in stone, because one of the challenges is once you go to this scale, an algorithm may actually just not work efficiently anymore. Like you can sort of say, oh, well, I've got this algorithm that works really nicely on a terabyte of data. But when it goes up to a petabyte, it's harder to do. I mean, you can generate artificial data, but that's not always. It will give you an idea of how well your algorithm is performing, and they are doing that as well. But this at 600 petabytes of data, at the moment you can't. No one has the storage to simulate, to create the artificial data set and then query it. So these are sort of the things. So yeah, I mean, and as you say, just driving the telescope needs a supercomputer, and just combining all of this data needs more data science, more algorithms to just combine it, because as you say, like efficiently doing it and then moving it, getting that reduced sort of product, doing like effectively a map reduce, and moving it down to Perth in that instance, and then doing some more processing and storing it. Like those algorithms are not yet written. They're working on it because they have Pathfinder sort of prototypes. So the Murchison wide field array that I mentioned with 40 petabytes of data at the moment, that's one of them. And then there's another one that's run by CSIRO called the Australian SKA Pathfinder, or ASCAP. And they're doing similar things, and it's really complex. They have to bring in special hardware, GPU based algorithms to do a lot of it, because it is imaging, so it's a lot of parallelizable problems. But no, I think you'll see, certainly we've started working with, so the government has funded, not us directly, but we've started working with a group over in Perth where they've been funded at $65 million over 10 years. And we're going to start working with them to work on some of not that processing pipeline, but the next phase, the actual sort of more science phase of matching with all the other data sets that are out there, so you can understand what this thing is that you've detected. But I think there'll be scope, and there'll almost certainly be calls for private industry collaboration. So as I said, these are all publicly funded. They're universities, so they are resource limited to some degree, but there will be calls for industry partnerships in order to help process this data in a meaningful way. It can even just be stored, let alone analyzed properly. And then there will be analysis too, because astronomers are pretty good at algorithms, but I think the data science community has a lot to offer, because you view data in a different way. Like astronomers still have this idea of downloading all the data onto their laptop. So which is not going to work anymore. So I think that there's a lot of scope for collaboration and partnerships with industry groups in the data science realm, as well as obviously the hardware and all of those things that I talked about as well. But this project, it's like €6 billion. That's because a lot of it is run through Europe, but we're the hosts.
Right.
So it's a €6 billion project, and that's just the setup. So the ongoing maintenance and operations is probably a few $100 million a year. So there's a lot of scope.
I think we just got a question from Ray, so I'm just gonna read it out.
Mm.
So his question is further to discussion, is there any work to have AI to look at raw data in sliding windows to detect noteworthy events feature flag for priority investigation?
That is a very good question, and there is some. The raw data is harder because, as I mentioned, you do have a lot of these effects from the actual instrument. So, I mean, if in your AI you can sort of remove those by training it up correctly, then I think there is scope for that. And I know that certainly with the radio, the square kilometer array, and all of those systems, there is some work being done with AI and deep learning, but um, that's it's not really my expertise. But yes, I know there is some, and there is certainly scope to improve always. So that is an area, yeah, as you say, and the transient phenomena, the sliding window is totally what you need from a time temporal point of view.
The other question I was gonna ask, I suspect I know the answer already, is that using the edge analytic. So EDG, edge analytic. I think edge analytic seems to be has been really useful when um, in the IoT devices,
Mm.
physical devices, where all of those data are processed before get uploaded to the cloud. And I
Yeah.
suppose the reason why I asked that, I raised that is because you were saying that the telescope have to be in a super far isolated area,
Mm.
and then it sounds to me what you were saying earlier is that transferring the data using the fiber optic. Hence, it got me thinking that what about the age of the analytic? But I suppose the answer that you will be telling me is not possible because of the amount of the data that have to be processed, making it unrealistic.
Um, I mean, I think it's an interesting question because, and I wouldn't rule it out completely. But basically, what you need to do, so as I said, you have thousands of these little antennae around. So if you treated that as effectively as an edge device, as an IoT device, then you certainly could imagine some processing there. And in fact, it has to be anyway, because in order to combine the data with all the other antennas nearby, you need to do that. So there does need to be some as well. And I think their basic model is really almost like a cluster-based system and a cluster of cluster-based systems. So you have like a cluster of these antennae, and they have some edge processing, and then that sends it to a more centralized system on site that does some more, and then sends it down. I think that's their basic model. So it's not unrealistic. It's all challenging, and I think at this stage, even though I said at the end of the decade, a lot of this compute, because the compute power is not there, a lot of the algorithms need to be developed now, and it's in progress. But I think at this stage, all comers would be welcome with ideas um, to 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 work on that sort of project.
Fascinating. Certainly have learned a lot. My final question for you. If anyone else have any question, please feel free to jump in. Ask away. My final question for you is that have we observed anything of the event that is similar to the Don't Look Up Netflix movie that we should be aware of?
Nothing that's serious. I mean, I must say I haven't seen the movie, but I do know the basics, and they did get some astronomers, some astrophysicists as consultants for that movie. So the only thing that, as far as I know, that's not accurate is that astronomers don't really wear corduroy jackets. But otherwise, nothing that serious. Certainly, there are asteroids that we are monitoring because they do cross the path of the Earth's orbit, but they have quite sophisticated models that can determine, they know the Earth's orbit around the sun and all the other planets. So you have to take into account all of the other planets and the gravity and all of these things, and then the motion. And it comes down to probabilities. And so the worst case one is like a 1 in 20,000 probability of impact with the Earth and usually they're at a few hundred meters to a kilometer scale, which is smaller than the one that wiped out the dinosaurs 65 million years ago. But that's, I think, 1 in 20,000 probability in the next 500 years or something like that. And so basically the Vera Ruben Observatory, and there are several other facilities around that are constantly looking at these sorts of objects and tracking them over time. And then because the more observations you have and the positions you have across the sky, the better you know how likely it is to hit Earth. And so at the moment, if you see something on the internet that says, we're in danger in 2024 or something, and you're like, take it with a very large grain of salt, because the chances are still very, very small, and probably another few months worth of data will rule it out. Always more data helps.
Putting the joke aside, one of the things that I find curious to know is, obviously in the Hollywood movie, American is always the one who have to face the natural disaster, hitting of the meteor, killing the alien. They always go to America first, and course. They are the one who first to find out. But in reality of these, it sounds to me the different agencies are sharing the information. So if any one of these find out this sort of noteworthy event, it sounds like most of the government agency would have shared the information.
Definitely. Definitely. And in fact, in terms of the asteroid searching and everything like that, it is very much a US based thing, because they have a lot more money and everything like that. But there's a lot of work being done in Europe and in China and Japan, in particular. Like a lot of people are interested everywhere, but that's where a lot of the money is, and some in Australia, because we are uniquely placed because we're in the Southern Hemisphere, and in South Africa. They're the two sites of the Square Kilometer Array, South Africa and Australia, but also and South America they're the three sort of places where there are telescopes to look for these asteroids. But yeah, astronomy is a very, very much an international science, more so than many other sciences, in fact, because it kind of has to be. It's resource limited from the point of view of people and hardware, and the good places to, like, you couldn't go out in the middle of Brisbane or Sydney and observe some of these really faint galaxies. Just not possible. Too much background light. And so international collaboration is essential. The Square Kilometer Array connects Europe, the US, China, Japan, Australia, New Zealand, South Africa. There are several other African nations as well, where it's being used, and in South Africa too, where it's being used as a development opportunity to teach STEM, and critical infrastructure is going there. So I think the chances of only the US knowing and not sharing it are pretty low, because the word gets out. The astronomer grapevine is much more reliable than the regular internet grapevine, and so I think we'll be fine.
I got a dumb question. Why is the location of Australia as a southern hemisphere is good for having the telescope?
It's primarily because it's so radio quiet. So in the outside of Western Australia and in sort of the heart of South Africa and a little bit of Botswana as well, there's no development. And in fact, it's desert, so there's not even real possibility of development. So there are radio quiet places, for example, in Russia. And there's an interesting question on the chat there from Ray. But there are places, but there's much more potential for development around them. And China as well. So China wanted to host the SKA, but it's just too densely populated, and the radio interference is just too loud, too great. So that security, is there concern around state actors interfering? Probably not from the science point of view. I mean, there is always a risk, but in most countries involved in this, it is a question of prestige and understanding the universe first, and being first is a big deal. But there's always a risk, and particularly because you're dealing with infrastructure that is incredibly powerful. So to not sound too blasé, too glib about it, you could imagine someone trying to hack in and just run Bitcoin mining because here's this massively powerful system that could do that. But, in all seriousness, we are always very wary of security holes and, or point to different parts of the sky. Ray, do you mean trying to drive the telescope to look somewhere else?
Yeah, sorry, I'll come in because I can't type too well. So there was some urban stories about state actors actually taking control of some satellites and big space satellites and so on, more for a proof of concept and things being lost. So just concerned that should there be not necessarily an open observation, but something where we wanted to look on the moon for something in particular, that someone was landing something there, and that became a motivation to point it somewhere else or interfere with the data from that regards. And the dilemma is with most systems, they're geared towards flexibility and openness and convenience of getting data. The problem is that then leads it to some other hiccups as well.
Yeah, for sure. I mean, data security is still an issue, and data control. And yes, I have heard those stories, and some of them are not entirely mythical. There's certainly been attempts, but the one thing for example, the moon is heavily monitored by not just NASA, but and a lot of those things, the US military has actually got far better telescopes than civilian astronomers do. And, we all joke. So I don't know if you're online when I was talking about the James Webb Space Telescope, but basically it's a telescope. It's a 6.5 meter mirror. In fact, it's a set of smaller mirrors all combined together. And that's too large to fit inside a rocket. So you have to fold it up and then take it out into space and then unfold it in this amazingly precise way. And we always joke that the only reason why we even considered that this is possible is because US military has already done it. And they have, one of the next space telescopes to be launched is called the Nancy Grace Roman telescope. And it's not a large telescope. It's 2.5 meter mirror. But it's one that the US military donated. So because they just had it lying around. So that sort of gives you an idea that there's a whole other level of stuff going on. So from that point of view, then state actors would be an issue. The hope, perhaps naive, is that for many of these other systems, state actors, bad actors would not be such a problem. But yeah, we have to be vigilant. There's no question that data security is just as important here. I mean, we're not talking about personal information, so that's the big caveat. So when there's personal information involved, you've got real issues. When it's ones and zeros, really talking about some far off galaxy or some supernova or something like that, and it's less critical. But you don't want things to be corrupted either. You don't want someone to come along and inject bad data in, making it look like there's some signal that is not there as well.
Fascinating. Thank you so much for this presentation. I don't think I have any other question. Ray or Aberal, you guys have any other question for Simon?
There's just one. As that you're working with Cisco, I presume there'll be some pretty good compression algorithms that you could have with the ASCII headers and so on. That would give you some little gain back, perhaps, with regards to the bandwidth. But
yeah, no, it's true, and we do manage the compression as much as we can. The biggest challenge actually is the binary image is the largest component there. But yeah, we are, and Cisco certainly ran into all sorts of technical challenges trying to get a lot of this to work, and I know that they ended up bringing it was the multiple collaboration. IBM were involved. A whole lot of very large companies were involved in the data transfer, and some of those compression questions were definitely there because you need lossless compression, and so So hopefully we get something beneficial, like a better lossless compression algorithm, for example.
Wonderful. Thank you so much again. And,
no worries. My pleasure.
Learned something really interesting and fascinating today. Thank you so much for this.
No problem. My pleasure. My pleasure. And as I said, I'm happy to make my presentation available. And if you contact Jason and with any future questions, he can forward those on, and I'm happy to take any questions at all.
Wonderful.